Hello and welcome back to another video. Now in this one we're taking a little step into the complex world, or the world of complex numbers, and we're trying to have a look at what this thing is here. So it's I to the power of I. So we raise I to the power of I, and recall I is just this imaginary number that allows us to solve some quadratics and other equations that have no real roots. Okay, so to begin, we recall that any complex number can be written as follows. So x plus iy, and that's where x and y are real numbers. So this is any complex number. Okay, but we also know that complex numbers can be written in something called polar form. And this is sort of introduced by Euler in 1700s. And he said that not only could we represent it in this Cartesian way, x plus iy, but we could represent it in a polar form as follows. So r, which I'll explain what that is in a minute, cosine theta plus I sine theta. Okay? Now, what is r? Well, r is the modulus. So that's the distance from the origin to z. I'll write that down. Distance from O to Z, and we can easily find that using Pythagoras. And theta is the argument of Z. Right, and this is something that lies between pi and minus pi. Okay, and this is the angle from the x-axis up to Z. So I'll write that, angle from x-axis, or rather, I shouldn't say the x-axis if we're in the complex world, I should say the real axis to z. Right, so with that in mind, let's try and put I in polar form. Right, so we've sort of reminded ourselves of this polar form of a complex number, and this is sort of how it works. So let's draw the complex plane, or Argand diagrams as they're called, named after a mathematician called Argand, obviously. This is the real axis, this is the imaginary axis. And if we take a look at the number I, this is nothing more than, well, it's got 0 real part, and its imaginary part is 1. So let me just write them in. So this is the real part, and 1 is the imaginary part. Okay, so that means that I on our complex plane is nothing more than this. So it starts at 0, that's here, and it goes straight up the imaginary axis. So this is Z. Okay, so that tells us that R equals 1, because this is 1 on the imaginary axis, and the distance from 0 to Z is 1, so R is 1. And what is theta? Well, it's the angle starting from the real axis that goes round to Z, like so. And this is 90 degrees, or pi by 2. So, and we check, does that lie in between minus pi and pi? Yes, it does. So theta is pi by 2. Right, so now using this polar form of our complex number, we can write it. So I therefore becomes, well, it's 1 times cosine theta, cos of pi by 2, plus I sine of pi by 2. And using this formula, we can also write it in an exponential form, e to the I pi over 2. And this comes about from Euler's formula. Okay, so now we've got that I equals e to the I pi over 2. And if you think about it, this sort of makes sense. We know that e to the I pi equals minus 1. This is Euler's identity, one of the most famous identities in all of mathematics. So if we know that e to the I pi is minus 1, then we must have that e to the I pi to the half, so the square root, equals minus 1 to the half. Okay, and this tells us that e to the I pi over 2 equals, well, the square root of minus 1 is just I. So we're almost there. Okay, so this is where we're up to. We have shown or we've sort of argued that the complex number I is nothing more than e to the I pi over 2. Now you'll remember that we're trying to find a value for this, I to the I. So let's substitute in our new value of I for the base. That's e to the I pi over 2. And we're still raising it to that power of I. Now what we do is we bring this I inside, just a basic rule of indices there. And we get e to the I squared pi over 2. And I squared is I times I, which is the square root of minus 1 times the square root of minus 1, so it's just minus 1. And we are left with e to the pi over 2 with a minus sign, because I squared is minus 1. So there you go, we have shown that I to the I is e to the minus pi over 2. And if you plug this into Euler's formula, you will indeed see that this is a real number. Thanks very much for watching, like, comment and subscribe. Bye bye.